start 4-1. So again, I didn't give you guys any homework for the weekend. And let's go ahead and start sharing. Okay, so we'll start with 4-1. 4-1 is titled Equilibrium. And I'll explain what that means in just a little bit. But equilibrium means there's no acceleration. So when a system's in equilibrium, there's no acceleration. So that means that your net force is going to be 0, because remember what force is. Force is ma. Also, what's going to happen is that because your net force is 0, your horizontal force is 0, and your vertical force is also 0. So Fx, Fy for those subscripts. But you can still rotate. There still can be rotation. And this right here is kind of a big formula. It's called torque. So the little t here stands for torque. It's a Greek letter, and we call it tau. Spelled like that. Why it's these Greek letters, I don't know, but essentially just force times radius. And this is the things that you guys will probably have experienced. Like if you're trying to, build something, like, if you're using like a monkey wrench or a screwdriver, typically the longer it is, the better or easier it will be for you to actually get something to rotate. If you've ever tried unscrewing something with a very short screwdriver, it's really, really tough. It takes a lot of force on your part. But if you do have something that's longer, then you probably don't have to apply as much force to get things to rotate. So this means that we use a component of the force that is perpendicular to what we call the lever arm. So, for example, I'm not sure what this is representing here, but say you're trying to lift something. I mean, maybe this is like a board you're trying to lift. So the force that you're applying will be perpendicular to the actual thing that's moving. That's what's meant by the perpendicular to the lever arm. So usually we kind of say that it's really going to be the perpendicular force times radius. Or if you have a force that's angled, then it's force times sine theta. Again, if your force is kind of like going like this, here's theta, that'd be a parallel force, that'd be the perpendicular force. And it depends on what you're what you're connected to. But you can see, like right here in this example, it looks like you're trying to undo the lug nuts on a tire. So there's a certain angle that you might form between this apparatus and the tire itself. But of course, we're looking more at the perpendicular force. Where theta is an angle between the force and the radius, or basically your lever arm. The units are Newton times meters. So this is just like work or energy. You could say a joule, I guess, but we really don't. CCW stands for counterclockwise. And CW stands for clockwise. typically we expect the counterclockwise torque to be positive. If you're going clockwise, we expect that to be negative. Just kind of the conventions that people use. But also, hopefully, you guys might recognize that usually when you rotate things clockwise, you tend to make things tighter. So you're kind of, I mean, you're applying force in either direction, obviously. But when you rotate things to the left or counterclockwise, you tend to loosen things. Not sure if that helps you understand whether it's positive or negative, but just know that counterclockwise is considered to be positive torque, clockwise negative torque. So let's try a problem. And then after we try a basic one, I'll have you guys practice some basic ones also. All right, any questions so far? Nope, okay, well, let's keep moving. Okay, you're meeting the parents of your new special friend for the first time. I don't know what special means, but anyway, after being at their house for a couple hours, you walk out and discover the little brother has let all the air out of one of your tires. That's not good. Not knowing the reason for the flat tire, you decide to change it. You have a 50 centimeter lug nut wrench attached to lug nut as shown. So this right here is 50 centimeters, or it'll be 0.5 meters, because you do want to convert to meters. If 900 Newton times meter of torque is needed, then how much force do you actually have to apply? And you also have the angle as well. So remember, torque equals your perpendicular force, or we'll say force times R times sine theta. So that's the actual formula we're using. So tau, or torque, is 900. The force that we want to find. The radius, of course, is 0.5 meters, meaning sine 120 degrees. So apparently forming a 120 degree angle, or basically, I guess your this is your arm, and this is the lever. So your arm is forming a 120 degree angle with the lever, and so you're trying to find the perpendicular force for that. And you kind of think about it. I mean, if you do have a lever arm like this, so again, this is a lever, and that's your arm. That's 120 degrees. So this is 60 degrees right here. Now, one thing to keep in mind is the sine of 60 degrees is the same thing as sine of 120 degrees. For those who haven't had pre-cal yet or trig, you'll learn about this. But whenever you have an angle that's supplementary, they'll actually have the same sine values. So once you have the force of your arm, which we're trying to find, but we're trying to find the perpendicular force, but you really want this right here. In order to do that, you have to do the force times sine of 120 or sine 60 to actually get this force. But this will be the force that your arm actually forms with the lever arm. So if you work it out, it's 900 equals force times 0.5, and sine of 120, I believe, is 0.867. Should get a calculator here. Yeah, 0.866 actually. So your force is going to be 900 divided by 0.5, and then divided by sine of 120. So you'll need to apply about 2,078 newtons to get this thing to move. So that's quite a bit of force, obviously. Sometimes you have a hard time, you can always call AAA as well. So, any questions about that example? Nope. Okay. That one should be a pretty straightforward problem. Let's see if you guys can try some problems right now. Let's see here. Yeah, 9 and 10 kind of deal with something else. So let's see here. So probably 5 and 6. Yeah. Yeah, let's see here. Yeah, 5, 6, yeah, 6, 7 for sure. And let's see this one here. Maybe we could do 3, 4, 5, 6. Yeah. So let's do 3, 4, 5, 6. So 3 and 4 are more conceptual. 5 and 6 will work out. Then we'll come back and we'll do this example on the seesaw. Then you guys do 7, 8, 9, 10 a little bit later. But let's do 3, 4, 5, 6, and we'll take about 10 minutes to do that. So again, you guys doing 3, 4, 5, 6. And I will ask, actually, and 7 as well. So let's redo that. So 3, 4, 5, 6, 7 actually is what we're doing. And I'll ask people in the groups to help us out. So 3, 4, 5, 6, 7. We'll do 4 groups. So 3 through 7. Okay, and we'll set the limit to 10 minutes. And you guys go.